Well, actually, the recording is not in progress, but Colin, we're
Okay, everybody, it is 12:03, so we are going to go ahead and get started to allow our speakers enough time to be able to present. So I just want to say good afternoon to everybody and welcome to the Department of Medicine's Grand Rounds. My name is Paul Hahn, and I'm one of the Internal Medicine Chief Residents. I would like to thank all of you for joining us today. Next week's Grand Rounds will be titled Pharmacotherapy for Type 2 Diabetes and Obesity, Recent Advances. This talk will be given by Dr. Simeon Taylor, Professor of Medicine and Director of the T32 Institutional Research Training Program in Diabetes and Obesity here at the University of Maryland School of Medicine. We hope you will all join us for that talk next week. For today's Grand Rounds, we have our Institute for Clinical and Translational Research at Medicine Grand Rounds, titled Cumulative Risk Factor Exposure and Cardiovascular Disease. We have the pleasure of being joined by a group of speakers led by Dr. Michael Domanski, Professor of Medicine in the Division of Cardiovascular Medicine at the University of Maryland School of Medicine. To briefly introduce Dr. Domanski, he received his MD here at the University of Maryland School of Medicine. He went on to complete his internal medicine residency at Penn State Hershey Medical Center and his cardiology fellowship at Vanderbilt University. Since then, he has had a distinguished career in academic medicine, leading and contributing to several landmark trials in cardiology, including the BEST, AFFIRM, TOPCAT, and FREEDOM trials. He has served as the chief of the Atherothrombosis and Coronary Artery Disease branch of the National Heart, Lung, and Blood Institute at the NIH, and as chairman of the Institutional Review Board at Washington Adventist Hospital in Tacoma Park, Maryland. He was also a professor of medicine in the Division of Cardiovascular Medicine at the Mount Sinai School of Medicine, serving as chairman of the Cardiovascular Clinical Trials Oversight Committee and director of the Heart Failure Program. Today, he is joined by Dr. Colin Wu, adjunct professor of medicine at the University of Maryland School of Medicine and mathematical statistician at the National Institutes of Health. We also hope to be joined by Dr. Jin Tian, adjunct professor of medicine at the University of Maryland School of Medicine and also mathematical statistician at the NIH. Please feel free to type any questions you have for our speakers in the Q&A box, and I will make sure that they can see them at the conclusion of their talk. Now, please join me in welcoming our presenters, starting with Dr. Michael Domanski. Dr. Domanski, I'll turn it over to you, and then whenever you're ready.
Paul, thank you very much. It's a pleasure to be here and to represent, pleasure for us to represent the University of Maryland Data Science Initiative as we give this talk. I will do several things with this. First of all, I want to discuss with you, begin by discussing the Data Science Initiative itself, its purpose, collaborators, collaborations, and some of our ongoing projects. The title of the talk is really the title of one of those projects that we'll share with you as an example. It's really a paper now that is hopefully in the late stages of review, and so we'll present some of the results from that, which we think are interesting. Okay, so first of all, some words about the Data Science Initiative. The Data Science Initiative really has evolved over the last couple of years into quite a large collaboration. The idea is for us to try to understand disease incidence that's based on cumulative risk factor exposure. You know, we talk about risk factors, but it's actually the cumulative exposure over a lifetime that is the damage done by the risk factors. And we're trying to quantify that, quantify the risk based on that cumulative exposure. The idea is to design risk mitigating strategies based on those data and to assess their probable impact. Of course, this informs the design of clinical trials, and it also informs policymaker analysis of health risk mitigation programs. It informs clinical trial design, and it also informs personalized treatment strategy design. So that's what we're about in terms of purpose. It's really a fairly large group of core group here at the University of Maryland. that includes both physicians, staff, and data scientists, all of whom now have appointments inside the University of Maryland system. NHLBI, Drs. Wu and Shin, and our colleagues from the University of Maryland, Baltimore County, Dr. Wang and Dr. Beck. The other things I'd like to just mention graduate students that have worked with us, largely from George Washington and Georgetown, and also from University of Maryland, Baltimore County, because they've really been important in data analysis and in working with us. And it's a awfully smart group of people that's a pleasure to deal with. We also have a series of collaborations now with a number of other institutions and research groups. The first three, Johns Hopkins, George Washington, and Geisinger, are involved with us in developing a clinical trial that really started here at Maryland, but now really involves those institutions and those people in trying to develop a thing called Concord, controlled coronary disease. I'll say a few words about that later when we go over our projects. We've also had a very nice collaboration with the Cardia investigators led by Don Lloyd Jones, who of course spoke here just a few weeks ago, and Val Fuster up at Mount Sinai, and also my old friend and colleague Mike Farku at the University of Toronto. So we have a number of collaborations in progress. We also have a number of projects that we're focusing on. You're going to hear about the first of these today, and indeed the talk bears its name. That's really a project now completed and leads to other things. So we'll be discussing that. One of the areas that we're very interested in exploring further is the whole self-reported race as a risk factor. What we're seeing in our data, what we've seen before in the SOLVE database, what we've seen before in the beta blocker evaluation of survival trial, is that self-reported race is an independent risk factor, independent of the other risk factors, and the full spectrum of mechanisms by which that's operating are clearly not known, but they're important if one's trying to individualize and provide precision cardiovascular disease treatment and risk prediction. We've also just finished a project on quantification of risk factor impact on loss of renal function. We're in the process of putting that together into a paper. And then there's the Concord trial, the controlled coronary disease trial, which we hope to put together in a way that NHLBI wants to fund. The idea, the sort of idea behind that study is that if we could keep LDL cholesterol near or in the neonatal range, we could do a lot to prevent coronary disease in the population. And Concord is sort of an evolutionary step. It's designed to have a surrogate endpoint, specifically atherosclerotic progression. We're going to try to show that we can reduce atherosclerotic progression by treating young people with LDL lowering medication, seeing whether that in fact reduces atherosclerotic progression as a surrogate. One of the interesting things about Concord is how do you quantify atherosclerotic progression? Non-trivial. Really our data science folks in concert with Joe Lima's group over at Hopkins, the MRI group, have really put together and George Washington have put together a composite endpoint that really has multiple axes of atherosclerosis progression. And what they're able to do is mathematically compare those distributions, in a treatment group and in a usual care group. We're excited about Concord. It's a work in progress, and we'll see if it ever gets funded. But those are major themes that we're involved in right now. Now, the study that we're going to present to you is actually, as I said, is a paper that's in review now. Hopefully, as I said, in the very late stages of review. We're hoping for it'll shortly be accepted for publication, but we'll see. But it's association of incident cardiovascular disease with time course and cumulative exposure to multiple risk factors. What we're interested in with this study, which uses the Cardia database, is trying to understand quantitatively the impact of multiple risk factors operating simultaneously over a lifetime at varying levels of severity. I mean, one can take a snapshot of risk factors that are present at a given moment, But that's not necessarily the exposure. Two people reaching age 40, for instance, with the same risk factor profile could have very different risks depending on what those risk factors have looked like over the course of time. So we're very interested in the idea of trying to quantify cumulative risk factor exposure over time. Okay, so let me continue to introduce that paper. I shouldn't have to convince this group that cardiovascular disease is important. It's certainly the most common cause of death in the world, the developing world as well as the developed world. In the lifetime of a child alive today, atherothrombotic events alone will kill more people than all the wars of history combined. I find that an intriguing statistic. I really spent some time looking that up some years ago and trying to put that together. And it's not just a little more than all the wars of history. It's several times. So we're really in the midst of a remarkable destructive epidemic. And we think that something can be done about that via risk factor control. In fact, substantial something. We think there's a significant percentage could be eliminated. Well, certainly cardiovascular disease more generally, not just atherothrombotic events, is influenced by a number of risk factors, some of them modifiable. There are indeed useful risk calculators available that incorporate these risk factors in their severity, but they use values that are snapshots in time and really may not accurately reflect the full destructive effect of cumulative risk factor exposure. So we've previously shown that area under the curve of LDL-C versus age is a metric of risk for incident coronary heart disease, and indeed that risk acquired per unit area is greater for younger than older individuals. The current study substantially extends that work. Using the 30-year follow-up of the Cardia study, and these studies are really, the being able to follow a cohort of patients over decades really allows us to say a lot about disease that certainly wouldn't be available otherwise. So this is a plug for big epi studies that have followed people for a long time. So our intent was to understand the relationship of incident cardiovascular disease risk to lifetime cumulative risk factor exposure generated by time-varying risk severity of multiple simultaneously operating risk factors. And to generate models that estimate risk of incident CVD and also its components, coronary heart disease, heart failure, and stroke. I would emphasize that the mathematics, which you're going to see in a minute, that underlie this really are quite sophisticated and involve machine learning to properly pick out risk factors that we should be studying. Our data science group, Dr. Xing, has developed a web application for this. If we present the cardiovascular community or the policy community with a series of equations, they'll be impressed and move on. But the ability to actually use those to make predictions, to say, gee, this is the risk that you have because of your risk factor exposure over time, and this is how you can change it if you can change these risk factors, is really worth a lot. And so they've developed a web application to facilitate simple and rapid computation of risk. We'll show you that web application at the end, and it's actually now uploaded at the NHLBI on the NHLBI's website, so you can go home and calculate your own risk or just plain play with it. So what we'll do now is move on. Dr. Wu is going to present the methods and results, and then we'll move to conclusions, then on to our app. Colin?
Okay, so next slide, please. All right, so let me go over the methods and the results. First of all, let me give you a brief summary of the Cardia study. So the Cardia study actually is a landmark study at NHLBI. It's really a great fundamental database for evaluating the early cardiovascular risk versus later events. So we had 5,115 black and white participants. They were recruited at year 1985 to 1986. So right now we actually had 35 years of follow-up. We are planning for year 40 exam. So it's a great study with a very long follow-up. And actually, the participants were balanced by race, sex, education status, and age at the baseline. So over a course, we have in this particular paper, we had the 9 in-person exam from year 0, year 2, year 7, year 5, year 7, all the way to year 30. And actually, we actually had a later data set for year 35 exam, and we are planning for year 40 exam. So you can see this is actually a very long-term study, and the retention is great because people work very hard, and you can see at baseline with 91% retention, but even after 30 years, we still have more than 75% retention, which is remarkable. People working very hard to recruit the participants, and also the participants really interested in participating in this particular study. So the contact even continues to be maintained with participants through telephone, emails, or regular mails every once in a while, and we had a lot of annual interim medical history ascertainment. Next slide, please. Mike, next, yeah. So let me go over the study outcomes, and for this particular, we actually had a lot of outcomes. For this particular paper, we considered the composite incidence of CVD. But actually, there are different components. There's non-fatal coronary heart disease and MI and stroke and also hospitalization, heart failure, and many others, as you can see, fatal or non-fatal. And the new events were recorded from baseline through August 2018. That's actually year 35 exam. During each examination, the interviewers and participants were questioned regarding interim hospitalization, admissions, and this and that. So it's really a complete study with a lot of things recorded. For participants who had been hospitalized or received revascularization procedures, vital signs, or so on, so they were recorded every 6 months, and the people really worked very hard to get as much data as possible. As you can see, over the last 5 years of the study, over 90% of the surviving cohort members have been directly contacted. So all the events are adjudicated, and we actually had the endpoint surveillance adjudication committee, and which the results are actually recorded as much as possible. Next slide, please. So in addition to the events, we actually have a lot of covariates considered. So let me list a few. So that we actually had the medication usage. This is actually recorded at every exam as much as possible. Physical measurements, lifestyle factors, medical history, and so on. There are a lot of biomarker data, laboratory data, also the imaging data by echocardiogram. And in particular, I want to mention the ones we actually use here. So I'll tell you why we use here, but we actually have lipid measurements of the total cholesterol, LDL cholesterol, HDL, triglyceride, diabetic, and so on. And blood pressure measurements, and blood pressure actually reported at every exam. So in addition to systolic blood pressure and diastolic blood pressure, we actually had the measure, the derived ones for mean arterial pressure, pulse pressure. So those are derived variables. So we also have the original variables plus the derived variables. And one thing about the analysis, which we pay attention, there are quite a few of those variables are actually skewed. For example, triglyceride, you can see it's actually skewed. So we use the log transform triglyceride. And in addition to all this original LDLC, HDLC, and so on, one issue in this particular study is how do we quantify, how do we quantify the longitudinal risk factors, because we have those measured over time. So that will be a key issue for this paper. So how can we characterize the time trajectories of each measurement over age, because they all measure at different time and this and that. we want to get a sense of cumulative exposure measure. So that will be the key issue for this particular analysis. So this is actually a really interesting methodology, statistical methodology paper. You can actually see that it's really not a trivial application of the existing methods in survival analysis. Next slide, please. Okay, so let me go into a little bit more details of the statistical analysis. First of all, one issue is that we have a lot of covariates. How can we actually decide which one to be considered, and how do we actually look at the longitudinal variables and decide which factors to use? So that's an issue which cannot be actually resolved by using classical traditional statistical methods. So that's why we have to resort here for machine learning method. But one issue about machine learning method, many people had the impression that it's a black box, and actually it's not. To us as for professionals, we know it's not a black box. So that's why I named here. So this is the so-called knowledge guided machine learning procedure. So the ones we use here, actually, each step we can have a clinical interpretation, so that we know what's going on. It's not a black box. So, for example, the first step, we actually select the influential risk predictors. So most of those variables we measure may not be actually important, so they do not make a difference. So the first thing is you want to shrink the pool of covariates into the ones you really want to focus on. You leave all those the majority of those variables unimportant for your endpoints, leave them out. The second one is there are a lot of factors, predictors, also highly correlated. For example, the imaging predictors and biomarkers and blood pressure, SBP, DBP, they're correlated. So you may have to separate those highly correlated predictors to different subspaces, because you put it all highly correlated together, the statistical model will not function correctly. So, and after all those are done, and then you can actually using the ones to build your prediction model. So that's actually a really interpretable procedure. So that being said, in this particular paper, we already done all those. So we focus on several ones we already selected. So I focus on step number 3. And the landmark, so the second question is for landmark analysis. If you look at the cumulative exposure, if you're an older person, just the pure fact you're living longer, so you have more exposure. So it's not fair to put them all together. You compare older person, younger person. If I'm a younger person, I don't want to compare myself with the older person who's 80 years old. So we know people live older will have a higher hazard for many other things, and even you have the low exposure over your lifetime, you still have higher hazards just purely because you're living older. So that's why one clinical interpretable approach here is the so-called landmark survival analysis to model. So to model the cumulative exposure of risk factor. In this case, is LDL-C, HDL, triglyceride, mean arterial pressure, and so on. So we use that. I'll go over a little bit more about landmark analysis. So the first thing is we use landmark Cox model. So if you model the time to non-fatal CVD events, we use Cox model. And the other thing is you can actually model each component of CVD. In that case, we use the fine-grained landmark fine-grained competing risk model. We can actually model the time to each specific event. So which factor affects CHD, which factor affects heart failure and stroke and so on. So because one thing about this landmark time is we say, okay, we pick year 8, year 40 as your landmark time, but you can certainly choose year 45 and many others. So we pick landmark for age 40 as example, just to show you. So this landmark analysis actually answered the question. Suppose you have a patient sitting in office who's 40 years old. You look at this person's accumulated areas of LDL, HDL, triglyceride, and so on. You say, what are those associations between those cumulative areas of those risk factors will have on your subsequent time to CVD event after age 40? So you're sitting there, you didn't have a event before, and what's the chance of for you to have a CVD event in 10 years after 40? So at age 50, 55, and so on. So that will give a fair comparison. You're not comparing yourself, you're 40 years old, you're not comparing yourself with another person who's 80 years old. So that's the landmark survival analysis. Since landmark age of age 40 was set at the very beginning of follow-up, so we actually say, oh, before 40, you have some cumulative observation window. We check your event after that. So you have observation window, then you have prediction window. So our landmark analysis models actually characterize risk exposure with development of CVD event during a follow-up period up to 28 years, which is 40 to 68 years. And in this particular data set, we look at everybody who's age 40, who had no event at age 40. So we had 4,958 participants. Next slide, please. Next slide. Okay, so this figure actually is an illustration of the design. So we look at everybody who's did not have the event before age 40, and people came in at baseline at different time. They have measurements 18 to 30 at the baseline, which is 1985 to 1986. And by age 40, 4,958 participants who did not have events. And then we ask a question, how do we predict their future events after age 40? So so for our data set, last outcomes comes at 2018. So we have the prediction window of very long time. So from about more than about 26 years for predicting events after age 40. Next slides. Okay, so one issue is how do we look at your cumulative exposure of events, your risk before age 40? You have many measurements. So how can we look at the cumulative exposure? So we computed for each person, we computed each person's specific cumulative areas of LDL-C, HDL-C, log triglyceride curves over age. The one method we use here is we're using the so-called non-parametric cubic spline mixed effect model for all participants. So this is the so-called blue prediction. Xing and I actually published a textbook about this. And for example, if you look at the top left panel, we have the LDL-C. The blue dots are the observations of this thing, and the red curves tells you the predicted LDL-C computed from the so-called cubic splines, and the gray area is the area under the curve. You can actually see this person's LDL-C is increasing over time, and also the middle part is HDL relatively flat. The right panel, top right, is triglyceride, also flat. And then we have the main arterial pressure and pulse pressure which change over time. So this is an illustration of how to compute each person's subject-specific area. I have to mention that the cubic spline is a very nice thing in mathematics because it's really not based on any given model. It's very flexible methods, and you can adjust for different shape of the curves. Next slide, please. So we computed everybody's area. Yeah. Okay. So once you have everybody's area and the overall exposure, remember the larger area tells you the overall exposure to the risk factor. So once you have that, we feed the multivariable Cox proportion hazard model to look at which factors lead to time to composite CVD events. If you want to know whether any of these factors lead to a particular subspecific events like CHDs and heart failures and stroke, and then we have to use the fine gray competing risk model. But we look at fit all this, look at the relationship between the risk factor, the overall exposures to those events occurred after age 40 years. We also adjust for sex, race, and other traditional cardiovascular risk factors measured. This is because we have to, in a lot of studies, and people found those are traditional risk factors, so we have to convince people by adjusting them. Those include history of CHD, body mass index, glucose, eGFR, and presence of diabetic, and so on. All right, so at the very end, we can develop a final prognostic event prediction model based on the Cox model. We can also do that for fine gray model after for this participant's risk profile at age 40 years. And we use the stepwise variable selections and so on. So those are included in the knowledge guided machine learning procedure. Next slide, please. Okay, so let me go over some results. Originally, Dr. Tian would like to present it, but she had this code, and so let me go over those results. Next slide. Next slide. Okay, so let me go over first of all some patient characteristics. You can see the study is well balanced between white and black, man and woman. And there were education, those educational levels, those are the classical traditional risk factors, and smoking, family history. At the bottom of this basic characteristics table, we also have the area under the different risk factor curves, so area under the LDL curves, HDL curves, log triglyceride, and so on. And so this is tells you that all the variables we hear, we actually use those for to build our model. And the question of how we selected those variables also selected from the earlier machine learning procedures. So let me go over the key findings. Next slide. Okay, so this is the central illustration, actually shows you the key findings of this. If you want to use one slide to represent everything about this paper, and this is it. At the top panel, left-hand side, we had the cumulative LDL exposure separated by quartiles. So from the lower quartiles to upper quartiles, you can actually see the cumulative LDL. So we started from age 40. Remember, we selected landmark age is age 40. We see what's the event chance you have event after age 40. So we select that, and you can actually see if you have over higher cumulative LDL, your risk is your chance of having CVD is getting higher. You're the highest. By the time you look at this top right panel, by the time of age 55, if you're an upper quartile, 88.1% of participants had event, so which is remarkable compared to the lowest quartile. By the time of age 5, only 2.7%. So it's a huge separation. You can actually double or triple your event rate at age 55 if you have high cumulative LDL before age 40. And the right-hand side, the top panel shows you triglyceride, which is also a clear separation. If you have top right corner, upper quartile 8.9% versus lower quartile, 2.2% chance of having CVD at age 55. And the two lower panels tells you the main arterial pressure and pulse pressure. We didn't show the HDL because HDL was not that much significant. But one thing about the main arterial pressure for blood pressure is that you have three lowest, second, and third quartiles. They are also glued together. Even the higher blood pressure is not as good. But if you have a top quartile blood pressure, your chance of CVD is also very high. It goes to 11.3% by the age of 55, compared to the lowest quartile is only 2.7%. Similar story can be said about pulse pressure, but this is the key finding for this. If you look at each of these cumulative exposure. So next slides. All right. So to recap, central illustration display the incident CVD after age 40 years as a function of time by risk quartile, showing both increased risk over time, also seeing increased risk from the lowest to highest quartile of total exposure. So those are illustrated in the figure. Next slide. Okay, so we will show next that lipid fraction, cumulative LDL and HDL versus blood measurements and other covariates are also important to look at the events. So let's go to the numbers. Next slide, go to numbers. Okay, so those are shown in this results here. So the left-hand side, I think are you missing one slide? Before that, there's a slide number 23.
Let's see, Colin, let me go back.
Yeah, you
Just a
skip
second
one
now.
slide. Go back. Oh, there's missing one slide in the middle.
We can probably retrieve
Sorry,
it.
Dr.
Give
Wu.
us 1
1
second,
second, Dr. Wu, yeah.
Colin.
Okay, so while you're retrieving, that's a slide number 23, Cox model for CVD risk, event risk. Let me just say that in words. So from the CVD event, we found that the cumulative areas of LDL-C is crucial for CVD. And in addition to that, the triglyceride, main arterial pressure, and pulse pressure also lead to higher CVD incidence. So those are all cumulative, those are very significant effects. And also, if you look at the other variables, and there are quite a few other ever smoke and traditional variables, family history of CHDs, those are also important. And in addition to that, there's race, self-reported race. So black race has a higher incidence, which suggests that we have to analyze if you those separate, because if we want to make precision medicine, you want to make precision predictions, and we have to go back to evaluate that.
Hi, Dr. Wu. I have your original slides pulled up here, the ones that you emailed me. If you don't mind, I'm going to share them right now.
Okay, so slide number 23. So that's right.
Can you see them?
Yes, Okay, yeah, so that'll be correct. So this is the one, if you look at the overall top over LDL, so higher overall areas LDL lead to very significant, lead to higher hazard. And remember, this is the area under the curve, and all this hazard ratio is unit dependent. So 1 unit increase of area of the LDL-C will lead to 1.04 increase. So HDL is protective overall, but not that significant, which is interesting to discuss later. But triglyceride is lead to increase higher LDL, and the area under the main arterial pressure increase hazard ratio and the pulse pressure. And so those are the cumulative areas. So below that, there are some other risk factor, traditional risk factor. We use the last observation carry forward. You can see race, it's a very big, very at the end of the table. And unfortunately, cardio only has black and white, and I wish we can have more race here because we'll represent the country right now. All right, so next slides. So to recap, we have lipid fractions, cumulative exposure to LDL-C and triglycerides was strongly positive and independent associated with CVD event after age 40. And there's some trends for HDL, but not that significant. And blood pressure, of course, shows the trend. So next slide. So next slide is that we want to see whether there are different risk factors for different type of events. So the left-hand corner of this table is for coronary heart disease. And the middle is heart failure, and the right model 3C is for stroke. You can actually see that different areas of risk factors lead to different type of events. So this is done by after machine learning and then we apply this competing risk model, fine-grained risk model. As you can see, LDL-C is area under the LDL-C curve. It's very significant for coronary heart disease. But if you, none of the others are that important. The blood pressure and others are important for heart failure and stroke. On the other hand, LDL-C is not really that significant for heart failure and stroke. So the take-home message from this table is if you really want to focus on different subtype of those events, you have to look at specific risk factors. That may be possibly explain why different race and may have different event rate, and race can be a factor, male or female can be a factor. If you look at male or female, that men are more likely to have CHD compared to black and whites, and they're more likely to have heart failure and stroke. That's compared the lower part for race. Okay, so next slide, let me summarize this a little bit. So the data show that the quantitative impact of cumulative exposure of CHD risk, CVD risk is different for different components. That's the first take-home message. For example, LDL-C is associated with CHD, but not the others. Blood pressure, those are highly associated with heart failure and stroke. For incident CHD, male sex was independent risk factor, so men more likely to have CHD. Next slide. Okay, so I'll go back to Dr. Domiansky to give conclusion. I'll show you some of this app later. Dr. Domiansky.
Got it. Okay. All right, thanks, Colin. Well, so in this paper, what we have is a 30-year follow-up of the Cardia study used to quantify time course and severity of each of the risk factors, considered in the analytical context of all of them operating simultaneously, and how they affect each CVD component and the composite endpoint of cardiovascular disease. This is, it's really quite a remarkable analysis. It also shows the complexity of the risk factor picture that we're looking at. It really is somewhat different it's different for different components, and it's somewhat different for different racial groups. And I think, that's very important if we're trying to treat specific patients. And also if we're trying to design public health programs that are intended to mitigate disease in these populations. Certainly, the quantitative description of the link between risk factors and CVD informs the construction of individualized CVD mitigation strategies. And of course, trials to study them, and allows you to make some assessment of the public health impact that you're likely to have with changes. Now, these, this mathematics that underlies this is complex. And for most cardiologists and probably even more policymakers, if you tell them to go take these data and somehow, do something with them, I think you'd find the stuff gathering dust on a shelf. But what's been developed to try to do something about helping us compute the risk in a practical way is the development of an app, which in point of fact, anyone can use. This app is now up on the NHLBI website. You'll be able to go home and play with it if you're interested. And Colin, I'm going to go to the next slide, and if you'll go over this app and how they can use it.
Okay, so this is actually a Shiny app we created. So you can actually input your data and download your overall longitudinal. You have more than one measurements of risk factors. You put them in and download them there. And then you also have to input answer some questions in part B. And then the outcome you can actually record, calculate this thing. So I'll show you some examples. Next slide. All right, so this is a case. We have two cases, and case 1, case 2, we put them side by side. Let me explain each one separately. So this is a little too small to read, and then let's go to the next slides and let's look at case 1. Okay, case 1. So this, you input your record. So you have 1, 2, 3, you have 7 measurements of LDL, HDL, triglyceride, and MAP, and so pulse pressure. So you enter you upload the file, and then it goes in, and we recalculate. So the program recalculate the area under the curve before age 40, and you have the area under the curve, and right-hand side to the estimated area under LDL, HDL, log triglyceride, and so on. And then at the left-hand side, part B, you enter sex, race, and have you ever attended college, and so those are the variables we selected. You enter that. And then you hit run, you get this estimated cardiovascular disease risk. So you are 40 years old, and I have to say that this is a landmark age for 40. If you're 45, you have to recalculate it. So you go in there, and then you say, okay, my chance of age 55, and what's my chance of having CVD? And if you're age 50, your chance is 7.1%, age 60, 18.25%. It's pretty high. You say, oh, how come I have such a high chance of coronary heart disease and CVD? That's because if you look at your LDL, you're 38 years. You look at the top on right-hand side. You're 38 years old, and your LDL is 161. It's pretty high, so that's why you have a high event rate. So the case 2 is even if you have a higher event rate, you also will increase your chance of CVD. Next slide. So this is another person who has a higher LDL-C level at each visit. Everything else is the same, but your higher LDL-C, you look at your LDL-C when you reach age 35, your LDL-C is 193. It's sky high, and then you say, okay, what's my chance of having CVD? Your chance of having CVD, you're 40 years old, you're a young person, but your chance of having CVD by age 50 is 8.8%, and 22% of chance of having CVD when you reach 60. So this is actually a very nice app. We if the paper is finally accepted for publication, we got a green light from the journal, and we'll put this publicize this thing so people can play around. Okay, so those are the two cases. Next one. I think I'm done. Thank you very much. I see some interesting questions and from John. How did you select influential risk factors? Oh, this is one thing because we had the earlier papers and we use a sequence of methods in sequential order. We select those. So this is actually based on an earlier paper my colleagues published in Circulation Research. This is actually cited in our paper, how to select. We use sequential. We first using random forest, eliminate some of those, and then we fit lasso and other stepwise regression on that, and then we compare all this. We separate the correlated variable into different spaces. So I term this knowledge guided machine learning because I found this is actually a very nice procedure. So though we have a sequence of papers showing that. The second question from John, you indicate that you use machine learning, but it's not clear how you use machine learning. You describe classical models. You did not mention use of random forest or other MI techniques. How you determine which markers were independent of the others. It's an interesting question that's described in the procedure. I'm in the process of writing a statistical paper just to summarize this thing. We didn't mention machine learning in this particular paper because we only use the one we selected. We also talk with other investigators. So from Cardia, we have a sequence of important, there are some variables, traditional variables, they want to put it in. So, but we did use those variables select those. I can show you our earlier paper. Maybe I should work on a methodology paper. Next question from Alan. Cardia also has a genetic data. Let's see, Cardia Genetic does the introduction genetic data such as polygenetic risk scores, which can be considered life. The answer is yes. We may want to consider genetic, but this is too much for this particular Cardia for the Jack paper. Yes, we need to include it. It's interesting because for Cardia we have those genetic data, we have behaviors, and those are all different things and there are different risk factors. Genetic, you couldn't do anything, but you can change your behavior. And also we have subclinical outcomes, those are imaging and so on. So putting them together, it's a very fun project, which goes beyond what they can handle for Jack, right? We have a convinced Jack reviewers, so we have to make it as simple as possible. So next one, is there additional role for calcium score? Yes, in this calcium score is yes, but calcium score could be a phenotype or subclinical phenotype. So, so that's when we consider. So that's when we design the clinical trial. So, calcium score may not be a risk factor, maybe a risk factor, but we look at the things you can change. Calcium score, you may be able to change it, but yes, we should include that, but maybe that's a subclinical phenotype. Let's see. I see a lot of, did I miss?
Yeah, Dr. Wu, the next question, yes, is there consideration? Yep, that one.
Is there consideration to measure the levels in this study group? Mike?
Yeah, no, that really was not, that wasn't included in this study, but given what we now know about Lp(a), that would probably, that well may be an independent risk factor that we should be including.
Yeah, next one is what factor explain male-female differences at population level? It's a very interesting, this goes to genetic also. It may have different people have different diseases. Male have more chronic heart disease compared to female. So,
but you know, it's very interesting. The male, female, and also the black-white difference really is unexplained. I mean, it's not that the black-white difference, for instance, is operating through other risk factors. It truly is independent in addition, and it's not explained. And there's some, pretty erudite science that it would be erudite science to explain it.
Yeah, here's a question maybe from Lawrence, which maybe is a good question. In order to calculate area under the 40-year-old age, you need a great deal of data before age 40. How do you obtain that data? Yes, we for cardia we have 6 or 7 measurements, or some people have 3 or 4. So we can compute it using B-splines and so on. But if you don't have it, it's highly correlated. You lose a little bit accuracy, but it's not too bad. You need to have cumulative measurements. But if you don't have it, you can use your current one. Which is still okay. We have electronic health record right now. I think in the future we have multiple measurements. Yes, it's a great question. The risk assessment apps will be a useful tool. Are there any patient education tools? We haven't done that yet. We started using this and we try to publicize it. We try to educate people in our institute, right?
One comment that's worth making, though, it is true that there are a lot of data that are needed to make these calculations. I think one of the things that's happened is this era of electronic medical records. That sort of extensive data is going to be available on a lot of people.
Here's a good question from Chaz. Great question. Can you comment on major difference between your risk calculator and Framingham score calculator? Yes, Framingham score only use the measurement one time. If we use cumulative, we cannot use Framingham because Framingham putting age and everything together. If you're older, you always have higher cumulative exposure. It's highly correlated. So we have to use landmark age analysis, which is not the one using Framingham heart score. If you're 40-year-old, your exposure is different from 80-year-old. 80-year-old, even you really have a great lifestyle, you're 80-year-old, you have higher thing. So that's why the Framingham score, I think, is out of date. Hope I answer this question.
Dr. Wu, actually, we're at 1 o'clock, so I think we might have to wrap things up. But I do appreciate you trying to go through as many questions as possible. I do want to say thank you so much, Dr. Wu, for being able to join us virtually from the NIH. And of course, thank you so much, Dr. Demansky, for presenting your work and for kind of showing us the innovative directions of this very exciting application of the data and data analysis. So we thank you both so much for joining. Thank you so much, everybody, for joining virtually and for your wonderful questions. We hope you all have a wonderful rest of your day and a wonderful rest of your week. And we will see you for the next grand rounds on Wednesday, December 14th. Take care, everybody. Thank you.
Thank you.
And Dr. Wu. Meeting.